All right, so I want to give a few examples of p-values and how they work. So example one, let's start with a two-tailed test. And the first thing that we're doing when thinking about this is we need to find the test statistic. So let's suppose it's positive, then you're going to find the probability of getting a larger value and then multiply that by 2 since it's a two-tailed test. If you happen to get a test statistic that's negative, you would be looking at the probability of getting a smaller value and then again multiplying that by 2. So let's suppose you have a test statistic of 1.35 and it follows the t-distribution with 40 degrees of freedom. Then what we're going to find is the probability of getting something larger than 1.35. That would be 0.0923. Within Excel, you could type in what you see there, 1 minus t dot dist, and then inside the parentheses you have the parameters 1.35, 40 for 40 degrees of freedom, and true, meaning you're running the cumulative value there. So then we take that 0.0923, multiply it by 2, and we get a p-value of 0.1846. So that would be an example in that case where if you have a two-tailed test, find the test statistic, find the area either to the right if it's positive or to the left if it's negative, and then double that. So here's just a image to go with that. Just looking at a distribution, could be a z distribution, could be a t distribution, doesn't really matter. But in this case, let's suppose it's t, right? If your t statistic were 0, that means it would be a perfect match with the null hypothesis and be sitting right there in the center. If the data are a little different, don't agree completely with the null hypothesis, you'll have a test statistic that's not 0. And in this case, let's suppose it was 1.35. That's just shown there. And then what's the probability of getting a t statistic or a t-value that's greater than 1.35? Well, that's the shaded area, the 0.0923. And then the p-value is just doubling that. So this is just an image to go with the idea. So then let's consider a different case. Let's suppose you have a one-tailed test. And here, we're not going to be doing this doubling process that we had in the previous example. So for one-tailed test, the p-value, if you have the statistic contradicting the null hypothesis, that would be the setting here. So find the test statistic first. Let's call it t for the sake of this example. If t contradicts the null hypothesis, then what we're saying is, so the null hypothesis is that mu is less than a particular value or less than or equal to a particular value. So contradicting it means that you have a test statistic that's positive, right? So falls out to the right. And then the p-value is the probability of obtaining a statistic that's larger than t. So again, if you're in Excel, 1 minus the t.dist value. So that would be a right-tailed test. Example 2 here, let's suppose you have a left-tailed test. So the null hypothesis is that mu is greater than or equal to mu naught. So for us to get data that contradict this means that our test statistic t is going to be negative, so less than 0. And then the p-value is the probability of obtaining a statistic that's smaller than t. So in this case, if you were typing this into Excel, trying to get out the value, it would just be t.dist and then enter your parameters. So the statistic, degrees of freedom, and true. So that would be a second scenario with a one-tailed test. Another scenario here is that you have a one-tailed test, but the p-value is coming from a statistic that's consistent with the null hypothesis. So what I mean consistent with the null hypothesis, let's suppose that the null is that mu is less than or equal to 10, and you get data that completely agree with that. It's consistent with that. So x bar is less than or equal to 10, let's say 8 here. So in this situation, if you had a right-tailed test, so that's example 1, your test statistic would be negative. Or if you had a left-tailed test, so example 2 there, your test statistic would be positive. In those cases, your data agree with the null hypothesis. And in this setting, the p-value isn't particularly meaningful. It's meaningful in that you're not going to end up rejecting the null hypothesis, uh, but depending on exactly how you defined it, I showed in a different video a few different definitions for p-value or how people might see it. But in this case, you might say that your p-value is 1, or depending on how again you're thinking about it, you might say it doesn't exist. But that's not particularly meaningful. In these cases, we are not going to reject. So the p-value isn't as critical in terms of assessing a precise value with it, whether it's 1 or doesn't exist particularly. So what is the rule for rejecting the hypothesis when using a p-value? So it's pretty straightforward. If the p-value is less than or equal to alpha, your significance level, then you're going to reject. If your p-value is larger than alpha level of significance, then you're going to fail to reject the null hypothesis. It's that straightforward, just comparing those two numbers.